Howdy everyone, Dr. Regev here. Just a few minutes about this paper. Before we dive in, this is a frequency estimation algorithm by Stephen Kay, developed in 1989, December of 1989. And I've used it many times in my career for both radar, lidars, calibration, and so on and so forth. And I'm going to hold a lecture about this with some code, examples, and so on and so forth. But for now, let's go over this paper pretty quick. So Stephen Kay, fast accurate single frequency estimator. This is the topic here, and he compares his estimator to another estimator that used phase unwrapping, and then linearly fit the phase, and obviously the slope is the frequency, but he avoids the phase unwrapping. This is the model. It's a complex sinusoid with a wide Gaussian noise. Then he assumes the SNR is large. That can yield an approximation that a part of this noise is taken out of this equation and introduced straight into the phase. And then once you do the angular operation, the arctangent operation, you extract this as is without the need to unwrap by using differential, or the difference between a sample at time t and a sample at time t minus 1. If you subtract between them, you will get two noises subtracted from each other, and you will get this omega 0 as a parameter that we need to estimate. Let's see that. There. If we take the difference between these angles, we will see that we have omega 0, the parameter we wish to estimate, and noise. These two noises together is a correlated Gaussian process. This is the least squares formulation for this problem, and he goes ahead and he takes this, or calculate this matrix, the covariance matrix C, for this colored Gaussian process. He inverts it, and now we will have a closed form type formula, if you will, or expression for the estimator. It only uses one sum. Inside the sum, we take the angle operation after multiplying between xt and xt plus 1 conjugate. Okay, that will basically give us this conjugate multiplication will give us the difference in the angle. That's the trick here. Okay, this is the conjugate multiplication. Now we still have the angle operation within each and every sum term, and we will see in the end that we can actually take it outside the sum, even though it's nonlinear. And we will see how. He goes on and shows us how in the appendix. Now this estimator has a closed form variance, which is the Kramer-Rao lower bound, but remember this is true only for high SNRs. So this is an efficient estimator, but only for high SNRs. We're well suited for calibration purpose, and in which we can control the tone, the amount of energy we invest in the tone that we are injecting, for example. All right, now he's going and comparing it into with other estimators, and he shows that his estimator is preferable by how much? By n over 6. So for large data records, this loss in performance can be substantial. This omega t that we have up there is given us in closed form. It's actually illustrated here in this graph. This window function, wt, sorry, not omega t. This term, very easy to implement, and this is the estimator. Now the last bit of the estimator is that this angle is removed from the sum, and it's just one angle operation behind the sum, so to speak, outside the sum. And this is a very efficient estimator in terms of computation as well. And here in the appendix, it goes about showing that these two are equivalent for high SNRs, which is the SNR regime that we're interested in this paper. And that's it. I will see you hopefully I will see you in the webinar, in the lecture. Thank you very much for listening, guys.